Welcome to problem 11. We have Q equal to 1 modulo 4, which means that square root 1 lies in FQ, or there is a square root of 1 in FQ, and we have the normal elliptic curve. Oh, I misread this the first time I read it. I thought I had to prove that A was B plus minus 1, and I really couldn't see that happening. But we have to prove that if L is equal to 3 modulo 4 and not equal to P, so it's understood that Q is the power of P, then they are equal. Well, first let's see what I think is the thing we should do. We should simply look at the usual automorphism. Now that is ugly. Phi. The point is mapped into minus x square root minus 1 y. If we have a point of order L to 8th, and exact order, so does phi of P. And we need to show that if P lies in this guy, then phi of P will lie in the other. It follows from our lattice if we have omega 1 and omega 2. And say we have P here, then all the powers of P, or multiplier of P, will lie on this line, and the line of the other points, phi of P, they are turned 90 degrees. So could they possibly be even? They may lie up. Oh no, they have the same modulo omega 1 and omega 2, as far as I remember. So it's coming up there. Here. So could they possibly be the same? I never expected that to be the case. Oh, that's just a real number. Positive. And then these guys have the same length, and there's a right angle here, so that means that A equals square root 2 halves, and then this angle is 45 degrees. Oh, 2p8, 8/4. That was a surprise that they could actually be the same. Oh, but this point, they are the same if the point is omega 1 plus omega 2 halves, and that is exactly a point of order 2. Lovely. So that means that phi of p is distinct from p if it doesn't have order 2. So let p be the one of the largest order, that's the one we usually do. Then phi of p has the same large order. So that proves that they are the same. Then we have to show that this does not hold if L equals 2, if it's of order some power of 2. Oh, then this comes into play. That was a surprise. I actually thought that sometime we had an example where the type was 2.8, 2.2 to the third, so this doesn't hold. Oh, the other thing is, up here, L needed to be equal to 3 modulo 4 and not equal to P, and I didn't find those exceptions, so let's work on that first. Where did I use that L wasn't, say, 5? In none of the examples we have had hitherto have we had so large orders, many points of so high orders, so there are no examples I can try on. Well, that escapes me. Let's go back to L. There's probably some knowledge containing this point that I need down here. There's also a point of order 2 down here, coming from omega 1 halves. So they won't all come from this. So there are points from this guy and from this guy. but they won't necessarily have the highest order, will they? So if we have one point up here, then we can go down here, or up here, with I times that same point. All right. If the point of maximal order as a power of 2 does not lie on the diagonal, then they will be equal. The two powers here from the 1 and I times, those coming from I times, from this automorphism. So that takes care of that. If the highest one occurs on this diagonal, so let's be specific. And that is the, call it Z. So the point via Strauss P function of Z point, its derivative, and that's the a maximal. No higher alpha. Oh, they just say A, do they? No, they say alpha. All right. Then we use I times Z to go into the axis. Let's just go into this axis. So we define a new point here. Z2 equals 1 plus I times Z. I wonder what will be the relation of that. Oh. When we go up here, at some time we will hit a lattice point or let's just say it's 2 to alpha, omega 1 plus omega 2. Doing the same here, we go square root 2. So when we just turn it upwards to vertical, then I need a bigger drawing here. This guy has length square root 2 to alpha times omega 1. And if we go in here, we end up at square root 2 to alpha I omega 1 and that's exactly where this guy will hit after 2 in alpha times. I think that my conclusion from this would be that it's the same number of times it takes for them to hit a lattice point. The guy we had was square root 2 I z and up here we had L 2 in alpha, 2 to alpha, z equals square root 2 omega 1 When you're not recording while seeing this, then you can probably see through the maze much easier than I can. We have order exact 2 in alpha. Then we take this point, and when we go up 2 in alpha, we already know that it's a lattice point, do we not? Two to alpha z equals square root 2 times some integer. Oh my God, I've lost it here. So I'll start all over. We are assuming now that this point has maximal order. And when we turn it inside, that's the same as adding I times it, just rotating. So when we hit a lattice point up here, let's say it's the first one, just for sake, then the next one should hit 2 up there. So let's use that on Z here. We have, now what was that? That was the point Z2 here, all right. Yeah. Two alpha times Z equals an integer. Some integer may be any integer. And then when we multiply that with square root 2, up here we get 2 times 2 alpha Z equals 2n omega 1. They cancel. So we prove that this point we get from going in here, Z2, it has the same order, but it may have half that order as well. Or a fourth, maybe. But is it possible that this guy hits a lower one than this? If these go out, say they have order 4, 1, 2, 3, 4, and then we go up here, take the sum, they may have half the order. If they have order 5, that's not a power of 2, of course, but let's just look at it. If they have order 5, then these might have order 1 less, or you can always choose an object, a point, so that they all lie in the same domain, in the same principal domain. And in that case, if we go up here, then they must have the same order. If we have one here and one here, they must all have the same order. So it's only if this one has, that there is a possibility of lower order. Or is there? Oh, then the order of this is twice as large as the order, no, half that of the order of this one. They lie on a line here. So when this one, if this one goes in the middle, which it should of course, because there's a point here in the middle, then the other one will hit one of these lattice points. So if, we know there are points on the diagonal, but of course the point of order 4 need not lie there, except they will hit at some time, of course. They'll hit half the lattice point at some point, but they may lie like that. But if they lie, so these are the maximal orders, then it might be so that the sum here has but that half the sum exists as well. I can see geometrically that this one has double order of these two, which gives alpha equals beta plus minus 1. But I can't do the geometry here. It'll be trivial as soon as I turn off the recording. Okay, now let's get back to the problem with L needing to be equal to 3 modulo 4. So I need to check what may be wrong. You know what? I'll make a little break and then I'll correct the error. I haven't made an error, but my poor reasoning here, and then I might get an idea to the other as well. I've looked a little at it, and here we need, of course, to take 2 to alpha of Z2, which I didn't do. And then 2 to alpha, they have 2 to alpha square root 2 z, and 2 to alpha of the modular of z equals, let's say it's just omega 1. Now where was, 2 to alpha of z means square root 2 omega 1, so that gives 2 omega 1. That was what I could see geometrically, but I just didn't do the algebra. I simply didn't compute where z2 would end. But it's worse than that. The connection between the complex plane and the FQ points, that would require that we define the Weierstrass P function giving FQ points, and that could probably be done in some in the fields I think it should be QP, where we take the closure with respect to the p-adic norm. But we haven't done any of this yet, so that's not the point. So therefore, the connection with the complex plane There may be something to it, but I can't use it the way I'm doing. And it's back to the drawing board, so I'll just end it for today, and then tomorrow I can hopefully record a little more. Hi. After a few days I'm back. I realized that I was using the structure of a lattice with Weierstrass P function, and we don't have that structure available here. So we have to use something that is specifically related to this isomorphism. And what I think we should use is the fact that if we apply phi twice to a point, then the first time we get minus x point square root minus 1y, and the second time we get x point minus y. So that's the opposite of the original point. Our problem was if we had we do have two distinct objects of order L, or two distinct sequences of points of order L, which of course means that we will have L squared. And then we have to prove that these occur to the same power. And my argument was that if one point was the maximal point, had a maximal order, then phi of p would have the same order. So we need to prove that it lies in the other. So if that's the point from here, we have to prove that it lies in the other guy. So assume that it lies in the same guy. So now we have a point order of p is exactly equal to L to alpha. And assume that phi of p equals np for some n. Then let's apply phi to this equation. Phi squared of p equals n phi of p. That was minus p, and this gives n squared p. Thus, n squared plus 1 times p equals the unit element, or the point at infinity. And that means that L to alpha divides n squared plus 1. That means that L divides n squared plus 1 This, of course, is congruent to 1 modulo 4. If n is even, and if n is odd, then it's congruent to 2 modulo 4. But the fact that it's even doesn't really matter. L should be able to divide it anyway. So let me just make an example. If L equals 7, and then n might be 2, 3, 4, 5, and n squared plus 1, 5, 10, 17, 26. So can we prove that L doesn't divide this number? Of course, this example. Now, they are all interesting, really. I'm stuck here, so I'll just take a break to get a new idea. I have no idea how to prove it, but I worked through some examples of n squared plus 1 and factored them, made prime factorization, and I used all integers from 2 to 50 to get their prime factorization. This gives 10, of course. And as you see, all the prime factors, it may be even, but all the other prime factors that occur, 5, 13, 41, etc., they are all equivalent to 1 modulo 4. not one of the prime factors is equivalent to 3 modulo 4 or minus 1. So it appears that it is exactly what we must prove, that if L is equivalent to 3 modulo 4, then it cannot divide a square plus 1. I'm due for my tennis training in a little more than half an hour, so I cannot concentrate on the problem. I'm not sure I have any idea how to do it anyway, so let's stop for now. I think I have solved the problem now. When Q is equivalent to 1 modulo 4, square root minus 1 lies in FQ. So this is an automorphism. So far is good. Now let's take the first part and assume that we have a generator of the largest subgroup of, or a power of L. So P, order P is L to alpha, and alpha is maximum. Then I looked at Q being phi of P. And wondered what kind of subgroup does that generate? The first thing I asked myself was whether Q was lying in the group generated by P. That's the first question, and I was able to say no. But to find the order, we need to check if any power of Q lies in here. So does for any n, NQ lie in there? If it's the case, then NQ equals MP. And they lie in the range from 1 to L to alpha minus 1. So let's assume this is the case for two numbers. Operating with phi on this equation results in minus NP equals MQ. And then we can multiply, I don't think it matters which we do. This guy we multiply by M, and this guy we multiply by N. M squared P equals MQ MNQ, and MNQ equals minus N squared P, which gives this equation is the unit element, and that implies that L to alpha must divide m squared plus n squared, which also implies that L so may this prime be the sum of two squares, and we know that that is impossible because L is equal to 3 modulo 4, and it happens for all the primes equivalent to 1 modulo 4, none of those modulo 3. Therefore, we go back, none of these guys lie in the group generated by P, subgroup generated by P, and therefore in its own right it will have order alpha, it is of course order alpha, but it has exact order alpha, L to alpha, and that shows that Q has order exact L to alpha. That was the first part. The next part, we do the same. We have the maximal and go through all of again, all the same, and we end here. But now the question is, in this case, L is 2, and it looks somewhat different. If m and n are odd, 2 will divide it, and if they are even, 2 will divide it. So that happens all the time. That was the problem that stopped me originally, though I of course only had unity here. The first case is mn being odd. Then m squared and n squared are equivalent to 1 modulo 4, and that means that the sum is equivalent to 2 modulo 4, meaning it's divisible by 2, but not to any higher order. So we have two divides the sum and no higher order. This only makes sense if alpha is equal to 1, to unity. And in that case we know we have another element of order 2. We have the elements of order 2 plus minus n point naught. That's 1 and 3, and U2 naught port naught. So there are two generators here, and they have alpha and beta equal to 1. So that was quickly. Next, assume that they are even. So the greatest power that exists in the two, let's call that 2 to gamma. So that m is odd, and n we don't know about. M odd. If they are both odd, then 2 divides this, and then it's the same gamma for both of them, of course. Then 2, but no higher power, divides here. And if n is even, then the sum is odd. So it's only 2 to 2 gamma. So that means that the highest power dividing m squared plus n squared or one higher. Now, what's all this about? This is all about the order of Q. We know Q has order less than or equal to alpha. I just need to take a break here to collect my thoughts. I'll just take a pause, a real break, and make a cup of coffee. Now the machine is working. The point is we have 2 to alpha divides m squared plus n squared. And that means that this is smaller, these are smaller than 2 alpha. So 2 gamma smaller than alpha, or 2 gamma plus 1. Oh, that should be an alpha. This is a little weird. Oh, I hadn't seen that number 2 coming, really. I thought it was 2 to gamma originally. I'll have to think about that as well. Another break. I have developed a hiccup, so I'll stop analyzing L equals 2. What I want to do is to make a better argument in this case. if L divides m squared plus m squared, then in set L we have this equation, which implies this equation, meaning that minus 1 is a square in set L, which is impossible when it's equivalent to minus 1 modulo 4. So my previous argument was wrong. I feel I've hit the head of the nail with this argument. But the case L equals 2, I'm still confused, so let's stop it for today. Almost as soon as I turn off recording, I got an idea. This means that minus 1, or is equivalent to minus 1 modulo L. And that means that minus 1 is a square in L. And we know that's impossible. I've removed the microphone, so the sound was very poor there. Therefore, we can make a proof in case L is odd. So we take a point of maximum order, then phi of p is not a multiplum of p, but it has the same order as phi. So np has order L to alpha. P must have a multiple of that order then, of n alpha, but it can't be larger than alpha, or L to alpha, so it must be L to alpha itself, because P was the maximum one. Therefore, we have the first question that alpha must equal B. So it's left what can happen if the prime is 2. And I have to stop recording now, so we'll look at that. Now evening has fallen. I've been to tennis training and had a nap afterwards, actually quite a long one. And it's time to check to find out if we can prove the last part. If L is 2, prove that alpha and beta are equal or at most 1 apart. We assume P is a point of order 2 to alpha, so that alpha is maximal. And if sigma P of P does not lie in is not one of NP, if this is not the case, of course it must be odd, then alpha and beta are equal, because it's one of the another family, so to speak. And we do the same. it's a little strange. What can we say about beta at all if this just lies in the same group? Generated by P. Well, first let's analyze if it's possible, then what happens. Means the 2 to alpha divides n plus 1. And I see nothing odd about that. Or actually I do. If alpha is even, then it's impossible. Because this is a square, they cannot lie so close. So is n alpha is odd. Then we have 2 times 2. Oh, it's just that it divides n squared plus 2. It's not equal to n squared plus 2. So this is all wrong. We do have some elements of order 2. And of course the unit element itself. So you know what? Phi of u2 equals u2, and phi of u1 equals u1. No, u3. And of course phi of u3 equals u1. So they lie in they lie both in one of the guys here, in one of the groups generated by one element. And there must be another one as well. We shall somehow use that they lie in the group generated by we have. So let's assume we have two, or we must have two different. So we have G1 and G2 generated by some Q. And what can we say about this? I tend to think that this means that they lie in distinct subgroups. Because in each of these, that's what bothers me. In each of these, there's only one element of order 2, and in the group we have 3 or 4 altogether. Oh, of course, that's the sum of 2 of them. Now we're beginning to make some sense of it. I don't know exactly what the truth is yet. The maximal one can be generated, or any of these can lie in the group of maximal length, or maximal number of elements. And then only one will lie in them. And then one of the other will lie in the other group. Where did my arrow go? Here it is. So there are 3 possibilities for this and 2 possibilities for this. We have to go through them all. So A. U1 lies in G1, then we have another group G2 generated by phi of that's called 5p, which have the same order. that leads to alpha equals beta, and the same holds for U2 element in G. And the reason for that is that that U2 and U3 map to a different element of order 2. So we have, if it's that was O3, of course. If O2 lies in G, then we need to look at then we have the two possibilities. A, no, it's irrelevant. What we have to do now is the analog of the thing I tried to do here, but without the lattice, of course, only using, only using something else. And of course we'll then have that U2 lies in the sum, as well as in phi of G2. This is a little interesting. Maybe we should look at the generators. So G1 was generated by, let's look at P plus Q. What can we say about P plus Q? I can't say anything. All right. I'll put my dinner in the oven. It's chilling today, and then maybe I get an idea. I just got an idea. U2 and U3 have the same order. And U1 and U3. No, sorry, that's not what I meant. Order Q equals order phi of Q, and then I would like to show that P equals Q plus phi of Q. Plus minus. That was my idea. I have no idea how I should be able to do that. And now my rice is absorbing its water, and the chicken is in the oven. So let's look at this again and just collect. P had order 2 to alpha, and we assumed that the element of order 2 in that group generated by P was U2, and the other order was 2 to beta, which was effectuated by an element Q. And we assumed then that the element of order 2 in the group generated by beta was U1. And my idea was actually to look at this point. And we see that 2 to, why are we putting it in blue? 2 to beta minus 1 R equals U1 plus phi of U1. That's U3, so that's just, yeah, we'll write U2. And that means that R now, does it mean that R has order order 2 to beta? Well, we know 2 to beta is the unit element, point at infinity. But of course it might come before that. Then that should be to a power of 2, and then this guy should be unity as well. So that means that the order of R is exactly 2 to beta. So we have found a quicker way, if beta is smaller than alpha, to get to U2 than the other. That means that R lies in the group generated by P. No, that's not necessarily true, is it? There may be up to 4 elements collapsing each time we add an element to itself. So there are many points of order 4 that could give you 2. So I don't think that's true. Well, another break is called for. I have thought a little about the problem, and I think that I have been far too engrossed in complexity. We have a chain starting with P, which is the point of maximal order, and then I claim that the other one should be made of points starting with Q. The group I call G, the additive group of the elliptic curve, and then we have the points of order 2. So the first thing to consider is that the 2 to alpha of P is a unit element, so 2 to alpha times Q is the unit element. And that means that the order of Q is a power of 2. The exact order of Q here, the power of 2. And we need to find the order in G modulo the group generated by P. The question is, half the guy might that lie in the group generated by P? This is a point of it's of course equal to 2 to alpha 1 phi of minus 1 phi of P, and that means it's one of the points of order 2. And if it's one of these, then it's the other point of phi of it is the other point. So if I equals 1 or 3, and in this chain generated by P, there is only one element of order 2. So in that case, we have beta equals alpha. Then they actually are equal. Oops. They are equal to U2. Therefore, we look at the points before that. So we look at 2 to alpha minus 2q. In G, it has exact order 4, because twice the point is a point of exact order 2. If it lies in here, it has to be either or 3 times the guy. They're the only points of order 4, exact order 4, in the group generated by P. They have opposite sign, so it's and then this is so that's minus x point square root minus 1 by. I just need to set a parenthesis here. There we go. If, now what's that? It's phi of, oh yeah, P, that's x point y, x, phi of x, yeah. If they are equal, then x equals minus x. Which of course gives and we still have a field FQ where Q is not equal to 2, so that means that these are distinct. That's only possible if X vanishes. Which is a contradiction. So in this case, alpha equals beta, and in this case, beta equals alpha minus 1. I believe this finishes the exercise. It wasn't very difficult, but I really managed to make it complicated.